Briefly, I have not met everybody of you. I'm in Helsinki for 5 years now, but before that I spent 7 years at Easter, so you will notice a strong connection to the work that has been going on in Grenoble at the time, so just to make the connections here. And the current team that is working on the topic consists of 2 recruits, Christina and Bruno, that you have currently, or that you probably have met at the poster session, working with me in Grenoble. Then we have a mathematician, Matti Lassas. We try to tame him or train him to do a little bit of seismology to help us with some analytical work. Then we have the French partners, and from Germany we have participants from LMU and TUM Munich that are mostly responsible for the numerical wave propagation that I'm going to show you later in the talk. So as I said, this took kind of off in this room. I didn't quite manage to pinpoint when this Cargès meeting was. I think it was 2013 perhaps, or 2012, when I spent a couple of 2 weeks before the meeting in the US doing seismic fault zone studies in California. So this is the Eastern California shear zone. This is, at the time, was used a dense array across the Calico fault zone. And I was playing the correlation game across that linear array here, and I was retrieving these waveforms. Of course, this is well understood, but if scaled to the maximum amplitude of the entire field, this waveform feature kind of stood out, of course, and I couldn't quite make sense of that at the time. So I arrived late into that set Cargès meeting. I think it was the Monday afternoon, and when I entered this door up there, Stéphane Catelin was having this figure right here on that screen, and that of course reminded me quite nicely about what this feature is, namely a focus spot retrieved in an elastographic medical imaging context. So this is where this all started, and again this connects to what we have seen also this morning. So this is using these ultrasonic transducers, a speckle wave field in a phantom or in the human body is retrieved, so passively retrieved. So there is some techniques going on to actually retrieve the noise in such a wave in this full space. This is a record. This is again along X. The wave field over time, and if this is correlated, this focus spot emerges again in complete analogy to these features that I recovered across the fault zone. This has been worked out by Gallo with Stéphane at the time. Of course, you also see this is the far field correlation legs. Again, this is correlation time, and this is the space domain. And what this is used for, what this has been used for in imaging, is of course by looking at each refocusing spot, identifying that the width or the shape of that focus spot is proportional to the local wavelength. And by doing this passively at each point in this phantom, and also by migrating this refocusing down the Z space, this focus spot imaging has been confirmed in medical imaging, again, some 10 years ago, to be yielding compatible images with tomographic or time-of-flight images. I also learned with the conversations that, first of all, you have to reproduce something that looks similar to what people are known or believe there actually is, and then it's accepted that this new techniques also works, and I'm going to show you also something later for seismic imaging where I pick up the same type of thinking. So again, we have a slow and a fast medium corresponding to some soft and stiffer tissues in the human body or some other soft tissue here. I also like to point out that before this actually matured into a mature imaging technique, in a few years before that, I think it also took place in this, let's say, environment here that Stéphane, in this paper, he refers to seismology. Okay, so this is a focus spot in soft solids reconstructed from data, and he demonstrates in that paper the synthetics using seismology in order to understand and to model the focus spots in a soft tissue. So at that time, in the early days, elastography was alluding to seismology in order to get their imaging enhanced. I think we also learned this morning with this new matrix method that seismologists are taking what has been done ever since then, and you can think about what I'm going to show today also in that same context, that I see what people have been doing in medical focus spot imaging, and I think there are some nice opportunities here that we can also adopt in seismological imaging. And again, this elastrographic medical focus spot imaging has been applied since then in a progression of papers that I'm of course not involved in, but this is work by Stefan, using different acquisition techniques and also different types of waves in the human body. But again, the concept is always the same. It's universal. Also at that time, this is the first, in my opinion, the first focus spot that I'm aware of in the seismological literature. That was again also presented not in a focus spot context, but in the context of dealing with anisotropic energy flux. Okay, so that paper is dealing with a filter that wants to, enhance the circularity of the energy flux. So this is bad, and this is supposed to be good. So this was the focus of the paper at the time. And the focus spot was just showing for convenience, I think. But you see, or what I think I see here, is that these focus spots don't differ at all in terms of their shape. And this is also what I'm going to show you later, that the reconstruction of this thing is quite robust, and it doesn't depend too much on a fully isotropic wave field, which makes it quite convenient for imaging. So this slide is meant to be a introductory mind map, and there's a lot of stuff going on here, but I hope that at the end you have an idea about where this method is located in terms of the literature and in terms of the available methodology that has been around in seismology and elsewhere before. So this is a seismic focus spot that is reconstructed from dense array data. I'm going to show you this. So this is about 1,100 sensors that were deployed on the San Jacinto fault at the time. And this is the time domain spatial autocorrelation field that can be understood in terms of this time reversal analogy that has been introduced to us nicely by us 2 days ago by Matthias Fink. So we have the converging, focusing, and diverging wave field. This is again a commonly seen correlation gather that can be understood again in this time domain or time reversal experiment. This time it's not with a circular time reversal mirror, it's a chaotic cavity, but it's the same analogy here. So we have this refocusing waves that focus at time t equals 0 and then they diverge again. So it's this thing here at t equals 0, again the time domain spatial amplitude field spread out in space. It's that simple. It's just you have to get used to it. That even if you want to compute it, you don't have to really take care about computing all the correlation. You just really have to take the spatial, the zero lag autocorrelation. This is related to the well-known and widely used spatial autocorrelation field that has been introduced in '57 by Aki. And it was noted in 2010, I guess, by Victor Tsai, that at t equals 0, this spatial amplitude field and SPAC are, and now you can, start finding equivalent, the same, the Fourier transform of each other, but there's, it's completely related. So there's formula by Haney given ever since after. So this is the SPAC, again, in the frequency domain, spatial autocorrelation field for Rayleigh and Love waves for the complete tensor, and we can make readily use of these formula to infirm, for example, the phase speed, and this is what this method is about. So we want to use the shape of this near field amplitude features to get an idea about the local phase speed. There is something again, that is, in my opinion, associated with doing SPAC, and these are these sparse arrays. Again, this has been around for decades. It's just that I would like to invite you to think about it now in terms of this dense array methodology, and not to make some, just local measurements of a local velocity profile, but you really use it in order to spread out to make images. Related to that is a study by Prieto. He used data from all of Southern California at the time, and he used also like a SPAC implementation, and he takes all this far field, all this ringing of the Bessel function into account in order to fit the phase velocity. Again, it's the same if you want, but I want you to look at this, to look at only this part of the data, and this allows us to increase the depth resolution and maybe also the lateral resolution of this technique. I put this one up because this is the log coherency of the same thing, and there was an artificial or ad hoc damping parameter introduced at the time that was simply put in there to get a better fit of the data, and this is also what I have been using in an example that I'll show you right away. So again, I showed you this time reversal analogy on the centimeter plate or plug. This is again from the San Jacinto fault, dense array, 600 by 600 meters, but it's the same thing. You have this refocusing, focusing in diverging wave, and I'm going to show you that this also works for yours array. This is, I think, for 80 or 100 second period. This is the lag time. You see the wave diverging, focusing, and diverging again, converging, diverging again. But all I'm interested here is really in exploiting the features of this guy. So this is the first, let's say, imaging attempt to use this. Sorry, yes.
Can you explain exactly what you're showing? These cross correlations with one station?
Yeah, of course, you see. Yes, of course, yes. This is the reference station, and this is the spatial amplitude field with respect to that station. Yes, yes, yes. So the idea is to take every station in a dense array and take this as a reference station, compute the focus spot, measure the width, and attach the the J0 Bessel function obtained argument. This is the phase speed to that point. In the San Jacinto, that was already quite a challenging environment because you see that these spots are not circular, so they are oval. And what I did at the time, this was a 2016 paper, so I just made it. I tried to fit it as a function of azimuth, and I got this one out. But the overall idea is that we can actually use it in order to compile these images point by point. So there's no inversion going on. All you have to do is do this fitting and attach the obtained value to a given position, to a given sensor. And you can densify at your liking. So this is the average phase speed. This is this attenuation coefficient that I had to introduce simply because it fit the data better. This is the speed against the fast axis. This is the anisotropy, and this is the fast direction of propagation. And all these features here have something in common that we know about the local geology there. So it appears like by simply making this measurement or looking at this at these properties, we can estimate the anisotropy and also to get the phase speed in a simple single measurement if, let's say, the parameterization of this is well understood. I also like to point out that we can resolve like small scale features. So this is the misfit of a Bessel function model to the data. And this corresponds also to a like an inclusion here. So there may be also the possibility to really resolve features that are much smaller than the wavelengths. Given then the wavelengths, but which is done is about the size of this frame here. Okay, so these were kind of the things that we have been doing back in the days, and the rest of the talk is, or the second half is, that is about work that we have been doing in order to constrain and to understand the limitations of these methods better. This is what I'm going to show in the next few slides. It's this work primarily done by Bruno, and then towards the end I will show you the results from the EURES array application. So this theoretical numerical work is done using this time reversal setup. So this is the patch of sensors, of virtual sensors, or of sensors where we want to constrain or compute our focal spot, and we use the Axitra software to compute the Green's functions between each sensor and 3 components to each of these mirrors at the surface and at depth. And then we time reverse them, and then we correlate them, so there's no real backpropagation, but we simply correlate them with a sensor at the center in order to produce this converging, focusing and diverging wave field that I'm going to show you in a minute. So these are the Green's functions recorded at each receivers at different azimuths, and then if we do this correlation in order to mimic or reconstruct the refocusing wave field or the correlation wave field in this on this target grid, we can observe this classical seismological correlation function pattern, and again in reminiscence to these early elastography methods, the focus spot at the center. Again, this is just for education, if you want, for these different components, ZZ, ZR, RR, TT, and we have the, again, converging, focusing, and diverging wave field in the classical way of looking at it, and this is at different lag times spread out in the two-dimensional plane. You also should note that we are focusing on Rayleigh waves here. I should mention that. Rayleigh wave fundamental mode. That we have also some energy at the TT. So in the near field, at the refocus near field, we have also energy on the transverse component. Again, this is compatible what Haney and others have been showing for the SPAC method. We will continue with interrogating the ZZ and ZR simply because this is the most robustly obtained data, seismic data, and also because for love waves they have also an RR and TT component, so they cannot be separated in the near field compared to these compared to Rayleigh waves. I'm also going to show you later. This is a two-dimensional Fourier transform of these focal spots, and they can also be used in order to infer some properties of the focus spot. And you should notice that this is not, so for example here we have a 2 kilometer Rayleigh wave speed, but this peak is not exactly at 1/2 seconds per kilometer, because this has to do with the properties of the Bessel function. So this is not just the cosine Fourier transform, and you also see that at the center we have energy that is not what you would expect from let's say from a beamforming pattern. I may want to skip that in the interest of time. This looks unassuming, but this already contains a key take-home message that I want to take you home here. So if everything is good, so if we look at these high resolution or high signal to noise ratio focus spots in these different components, then we can use the near field distances, up to as short distances as you want in order to estimate the wave speed. That's what I think is the complementarity of that method, so that you really accept that you don't have to use, let's say, 2 or 3 lambda cutoff distances for far field imaging, but that you can really use near field, and near field now refers to the fact that we are close to the origin, close to the virtual virtual source, that we can use these distances in order to make estimates of the local phase speed. And again, we use this work that has been done previously. So this is the J0 Bessel function for ZR. It's J1 dominated, and we can demonstrate this here in a field where we are sure that there are no love waves, that we also retrieve the RR and TT component, but this is more of an demonstration. So we would like to know what is the robustness if the wave field is actually anisotropic, so if the flux is anisotropic. So we put different weights before we, let's say, do the refocusing game, and this is a very extreme case. This is the far-field beamforming pattern, and here you see what the focus spot looks like if in such a case. So the dashed lines are, or the dots are show the case for the perfect circular shape, and although the fit along the north and the east axis, so this is along the north and the east axis, doesn't look good, fitting the whole thing at once gives you extremely low errors on the true speed. So this is also, of course, compatible with what has been said before by Nakahara and others, that if you do the azimuthal average, you get, even in case of an anisotropic incidence, you get very good estimates, almost true estimates of the local phase speed. So averaging over azimuth helps. This is playing with P waves. So these are P wave mirrors at depth. In this left half, I show you that they're all firing at the same time, and this on the right-hand side is a 60-degree angle. So you see that this is still circular. This is again then the fit to the ZZ and the ZR. The ZZ has considerable errors for these different fitting distances, but the ZR component is absolutely unaffected by it. So even if you have vertically upwelling P-wave energy, the ZR component gives you a fairly good estimate of the local Rayleigh wave phase speed. It's a little bit different for the 60s for this oblique incidence. However, then the ZR component also still does a fairly good job of giving you at least a good estimate of a local Rayleigh wave speed, although the fit is far from perfect. So of course, if you apply the J1 function, it cannot fit the offset here that has to do with this obliquely incidence energy. We can, of course, retrieve dispersion. So we played with different profiles, and we see that we get a fairly good fit, of course, in a noise-free environment between our synthetic data and forward simulations. Again, the point is that if we look at this distance versus the or like the fitting distance versus the wavelength, we can go to really small values. So this is again what I said earlier, that we can really go to wavelengths that are large compared to the array. So typically, if you think about an array, you want to, as I said before, you want to have in your far-field imaging, you want to have your 3 lambda cutoff. So that may be this one here. But you can make use of all this data that you collected in order to just look deeper and to increase your dispersion curves to greater depth. And we also look at what happens if there is a little bit, 10% noise added to it. And from what we take from home from this is that even in quite noisy environments, if you cannot go to that small fitting distances, but around fitting distances of 1 lambda, 1 wavelength, you still get fairly good estimates, like here, of the local phase speed. So this was this is work that is finished. Before we move on to the data for US array data, I want to come back briefly to this refocusing in anisotropic media. Again, this is typically how seismologists tend to parameterize radial anisotropy using this Smith and Dahlen parameterization, and then you see these figures that we also seen for Alperae, I think, what was it, 2 days ago. And that's what I also did back in the days, 2016, for this San Jacinto, using this grid search over azimuth. But we want to have maybe a closed closed form in order to get, like a mature fit. And in order to do so, this is then the collaboration with Munich. So they are the developers of the Seismol software, and they implement true physical anisotropy in these solutions. And Bruno is now playing with modifying the SV wave speed in the vertical in this direction, playing with this epsilon parameter. So this is an extreme case, but of a truly physically simulated wave field in an anisotropic medium, and you see that this is traveling fast in this direction than in this direction. And then by working out these expressions, we are currently exploring, again, this is very much work in progress, to understand or to make use of this oval shape of this refocusing wave field, and these fits here, again, this is quite extreme. So the Smith and Darlin parameterization is for weakly anisotropic media, so that maybe would be this one here. But that also seems quite promising, that we can just, you take a station, take an estimate, and estimate the anisotropy from it. Of course, what we have to do next is how this competes against or how this does in terms also how this performs if the incidence is also anisotropic and if there are different directions involved here. So there are competing effects that will likely make our life not easier. So we'll now move on to big time data application. This is Christina's PhD project. And we will show you something that we have been doing for US array. And it's of course good because there are published maps, phase velocity maps for US array that I will show you, that hopefully convince you that this is actually worthwhile trying. On the other hand, US array has this feature that this has this rolling deployment, and there are all other things going on, including these very long periods where the mixing is of course not perfect. So there are good and bad things about trying this in US array. The first thing is, again, as I said, extending the dispersion. So this is a result from Lin et al., who has been doing a lot of imaging using US array, and he stops at 100 seconds using traditional tomographic methods. These are example dispersion curves, however, whatever quality there is, but the point here is that we can go to 300 seconds. So we can make measurements, however good they are. Okay, that's on a different page. But the point is that we can increase the resolution by the factor of 2 to 3 here. This is the point. Of course, all the work subsequently, if you find this interesting, if you want to do it yourself, will deal with making the measurements more robust, understanding what the wave field properties are. But the promise is that we can go and make more extensive dispersion measurements. This is just an imagery, like a zoo of focus spots for 100, 200, 300 seconds. And again, the idea is that there is information that we can take out from these blobs. Ideally, yes, there would be circular. We have to work on that, and these are these K-domain figures that I showed you, taken from the entire field, but this can also be used in figures like that. So if we want to understand what is the energy flux, again at 100, 200, 300 seconds, this is hum. By mapping out the direction of the energy and maximum energy and the direction of the minimum energy, we can obtain maps like that. And again, it would be interesting to learn or to discuss maybe with Ardoin what he knows about hum excitation at 200 seconds in certain areas of the globe. But this is just a side result. This is it. This should at least suggest that this is worthwhile pursuing, also with other dense array data. So these are Voronoi cells, but again, they are just delineating the position of each sensor. This is at 60 seconds. This is an example focus spot size, and this is done with the fitting distance of 1.2 lambda. So this is really just taking a few data of the diameter of the sides of that footprint here. And then you just take each sensor, you play that game, and you assign simply, really simply, you take the J0 function, you fit it, you look for the local phase speed, you know the frequency, and you compile that map. No tomography, no inversion, nothing. It's just the fit. And this is how it looks like compared to an established tomography method, 60 seconds by the group in Colorado, I guess, is it? And again, it's up to very fine details about, Snake River Plain. It should be quite convincing, as I said earlier, as the co-workers have been doing in elastography 10 years ago, that this is something worth trying. We now want to explore the sensitivity of the results. I'm tapering off here, Pierre, I know. So this was the map that I just showed you using the Z component data with 1.2. It's actually half of 2.4. I don't know if that means anything. Fitting distances. This is fitting distance of 0.5. So you see that the fits are getting a little bit more grisly. But again, my suggestion is to go to smaller and smaller distances in order to get high quality measurements. And then, of course, going to larger measurements, the fits become more stable and the maps become smoother. This has been done, I should have mentioned, with fairly standard noise processing. So there's nothing fancy going on. This was a 3 times standard deviation clipping. This was 1-bit clipping. So you see, of course, there's some variability, but the main features are robust. And also ZZ seems to be more, at these very long periods, more robust than the ZR component data. Okay, I'm skipping that, and I leave you with 3 slides about what I think we should be doing next, or what we're interested in next. The big question is to understand lateral resolution. So the more and more fitting you do here, the better, the more robust fits to your Bessel functions you get, but it also implies to smear over things, but we don't understand this actually, what this means at the moment. So we need to understand what the lateral resolution is like as a function of the fitting distance. And we will be playing with this dense array obtained in Finland, and you see here this is an intrusion, this is an ore body, so we have a really sharp interface here, and this is one of the target things where we want to play with this, and also when we want to augment this with numerical experiments where there is a sharp interface, but you see also that even at so this is at focusing here, but again related maybe to, what was it, iconal tomography, there is some relation that even in these zero lag spatial amplitude fields, there is some information about the medium. Again, this is again from the San Jacinto fault I showed you earlier. The fault runs like that, so there's a low velocity, and you also see that there are other features in that wave field at zero lag time, if it's not homogeneous, that seem to be related to the lateral velocity structure. Then we would like to explore the effect of the array shape and the directional incidence on phase speed estimates. So it's all good and well understood if the array is regular, if we take a reference at the center, and as I said, if we average, if we make a fit on the entire array data, even if the energy flux is strongly anisotropic, we get very small errors on the estimate. Now, in the light of this, we are now playing with making, looking at the aspect ratio. What is the, as a function combined with different incidence angles, combined with different strength of this anisotropy, and then looking also at this position of the reference stations within this configuration using expressions that have been put forward in the literature and that also Bruno independently verified. Let's put it like that. And then finally, we need to deal with imperfect surface wave focusing and the optimal processing. I haven't met Sven Schipkus before, but you realize these figures were on the poster. These are data from the Vienna Basin. This is on a 20 by 20 kilometer scale and 5,000 sensors. So, I mean, that is exactly what surface wave focus spot imaging should be applied to. And we see here again at zero lag time, I mean, this is certainly not a surface wave focus spot, but it relates to everything that has been discussed before also, like understanding the different wave field components, filtering out body waves and everything that we don't want to have. So I think there's a lot to gain here in order to optimize that. And we have been starting to do this, for example, by removing earthquake data from this US array data set in order to improve the fit, in order to, by removing disturbing body wave energy from these measurements. And with this, I thank you for your attention, and I'm happy to take your questions.